we're talking about calculus in this set of notes, and so we use calculus a fair amount in MSF 502, the valuation course, and let's see, and statistics and econometrics. So the calculus is basically a measure of instantaneous relationships. Oh, look at that square. Instantaneous relationships between one variable and another, basically instantaneous slopes. All right, so if we have x over here and f of x for constant, and this is just f of x is c no matter what x is. So if we change x from x0 up to x1, it's still equal to c. So the change in the c is going to be 0. So a change in the constant is 0. Over as x changes, the constant stays the same. Well, it's a constant. All right, so I'm not going to go through any derivatives or proofs. But we remember that if we have exponentials, x raised to an exponential power, the c goes down there and we subtract off 1. All right, so we can think of maybe f of x as 3 plus 2x squared. Take the derivative with respect to x. Derivative of that is 0 and bring down to 2, so it'll be 4x. All right, so I guess where do we have this? So when x is 0, we got a 3, and this grows quadratically. All right, so what we see right here is the first derivative is basically just a slope. So when x is 0, the rise over the run is 0 here, but as x gets bigger, the slope increases at an increasing rate. All right, so we can think of the first derivative as a slope of the relationship, and the second derivative where we take the derivative of that with respect to x, is going to be 4. So the second derivative is positive. So what the second derivative gives us is a measure of the curvature. All right, so this gives us a measure of the instantaneous slope, for small little changes around different values of x, and the curvature tells us how the slope changes over time. So if it's always positive, the slope gets steeper and steeper. So if we have some function that looks like this, right here, we have a positive first derivative and also a positive second derivative, because the slope is increasing at an increasing rate. So this is a convex function. So down here, what we see is that the slope is increasing, but at a decreasing rate. So what we have here is a positive first derivative and a negative second derivative. All right, so we will use these characteristics in calculus to show if something's a maximum or a minimum. And so I don't really want to get into this, but I'm going to talk about the chain rule. Chain rule is useful in economics and finance. Basically, it's a function of x where we can write the complex value of x as some sort of internal function of x. So if we want the derivative of this complex equation that is related to x, we can break it down into an easy derivative by treating this function as a variable, and then taking the derivative of that function with respect to x. All right, so an example, let's say we have a 2 period in life, and we have a lifetime utility. Lifetime utility, and we can break it down as additive and time periods. So we lived for time period today and time period in the future. These time periods could be decades, so it's not that sad. But what we like to see is some utilities work of consumption where the utility is increasing at a decreasing rate. So if we have the first derivative with respect to consumption, it's positive, but if we take the second derivative, we see it's negative. So it's the law of diminishing marginal utility, if you remember your microeconomics. All right, so one thing we might want to look at is how do we allocate consumption over time? So let's say we're given some wealth and that's all we have. So we're going to save by investing X units of consumption or X units of saving into a bond that's going to pay off R in the future, where this R is going to be 1 plus the risk-free rate. All right, so that's how we consume. So we see that X affects C0 and X also affects C1. So if we wanted to take the derivative of dV with respect to dx, how does lifetime how does lifetime utility change as we change our saving? One thing we can do is take the derivative of u with respect to C0 times the derivative of C0 with respect to x plus this delta, which is some parameter we put on the future. Hey, since we might be dead before the future, maybe this is some number a little bit less than 1. We care about consumption today more than consumption in the future. All right, so we take change in utility over change in consumption in period 1. And then we look at the change in consumption in period 1 over the change in x. All right, so what these are right here are marginal utilities. Period marginal utilities of consumption. And so we see they increase at a decreasing rate. Right, so we can write this as, let's just write it down as the marginal utility of consumption at time 0 times the derivative of C0 with respect to x. You look at this, and we take the derivative of C0 with respect to x, it's -1. Plus delta times the marginal utility at time 1 times the derivative of C1 with respect to x. Take the derivative of this with respect to x, derivative of this with respect to x, and that's going to be 1 plus the interest rate, or R. Okay, so this tells us, so the interaction between the change in lifetime utility is the marginal utility we give up by saving 1 extra unit of consumption today, and what we get in the future is 1 times R, 1 plus the risk-free rate, times the discounted value of the marginal utility in the future. So it kind of makes sense. So we'll talk about this maybe a little bit later in the course, but for now we'll finish up with this discussion, and next time we'll talk about partial differential, not partial differential equations, but partial derivatives.